Hi, my name is Jack, and this is my final project demo for my Fall 2025 Graph Theory course. I built a web app that overlays a weighted graph on a map of the WSU Pullman campus. The app is a mini GPS that uses Dijkstra's algorithm to find the shortest walking routes between locations. The idea is vertices are campus locations, like buildings or important intersections, and edges are direct walking paths between them with numeric distances as the weight. On top of that graph, I run a shortest path algorithm so the app can suggest an optimal route between any two locations, which are two vertices. The layout is pretty simple. Up here in the Navbar, I have the from and to destination fields and a distance readout when the route is found. There are also a couple links in the corner. The first one will take you to my portfolio website where you can see the rest of my projects, and the second link will take you to my code repository for this project with a more detailed write-up. The rest of the screen is the campus map with the graph drawn on top of it as circles for vertices and lines for edges. And up here in the top right are zoom controls with a label to show you your current zoom level. Each vertex also has a small label that shows its degree, which is basically how many edges are incident to it. When I hover a vertex, it also highlights all its incident edges, so you can quickly see how connected that point is in the network. Edges are drawn as lines between vertices. When I hover an edge, I show a little label at the midpoint that displays the weight of the edge, which in this context is the walking distance between those two locations. There are two ways to choose a route. First, through the navbar, I'll type the start in the from input. As I type, the app searches over all vertices. It ranks results by exact match, prefix match, and then substring match on both the ID and name. Then it shows the best matches as suggestions. I'll pick this as my starting point. Then I do the same thing for the to field to pick my destination. Once both endpoints are set, the app automatically runs the pathfinding algorithm. Here you can see the total distance of the shortest path in the navbar, and on the map, the vertices and edges on that route are highlighted. You can also select routes directly from the graph without typing. The first click with no route yet sets the start vertex. Clicking a different vertex sets the end vertex and recomputes the route. If a full route already exists and I click another vertex, that becomes the new start and I can quickly explore different paths. The map is interactive. It has features such as zooming and panning. You can use these preset buttons just for ease, or you can use a mouse scroll wheel for desktop. You can use two-finger scroll on a laptop and pinch for a phone. Whatever device you're on, you have the zooming capability without just these buttons, but you can also use these for ease. To do the pan feature, to pan around, if you zoom in, all you have to do is just click and drag, no matter what device you're on. Under the hood, I keep a camera center and a zoom factor in world coordinates, so all the vertex positions stay aligned with the image as you move around. For the actual pathfinding, I use Dijkstra's algorithm for a single source shortest path on a weighted graph with non-negative edge weights. The time complexity with a priority queue implementation is big O of V plus E times log V, where V is the number of vertices on the graph and E is the number of edges. Given a start vertex S and an end vertex T, the algorithm 1 initializes distance V to infinity for all vertices except distance S equals 0. 2 uses a priority queue to repeatedly extract the unvisited vertex with the smallest tentative distance. 3, for each neighbor U of the current vertex V, it checks if going through V gives a shorter path. If distance V plus the weight of V to U is less than distance U, it updates distance U and records V as the predecessor of U. 4, once all reachable vertices are processed, or once T is finalized, it reconstructs the shortest path by walking back through those predecessor pointers from T to S. Because all my edge weights are non-negative distances, Dijkstra is guaranteed to find the true shortest route between the two selected vertices. For my code, the graph is stored with a dictionary of vertices, a dictionary of edges, and an adjacency list. For each vertex U, adjacency U is a list of triples. Vertex V, the weight of vertex U to V, and the edge ID. That represents each incident edge, where E is equal to from U to V. When the start and end are set, I call my Dijkstra function with that adjacency list. It returns three main things: the distance map, the sequence of vertices on the path, and the sequence of edges on the path. To summarize, this project takes a real map of WSU Pullman, overlays a weighted graph where vertices are campus locations and edges are walking paths, and uses Dijkstra's algorithm to compute shortest routes. The UI lets you explore the graph visually through degree labels, edge weights, and interactive panning and zooming. In the future, I'd like to extend this by adding elevation or Z-level weight costs, accessibility options that avoid stairs, and support for loading different campuses or custom graphs. Thanks for watching my demo.